Welcome back to the video tutorial series. I think I called it that for EBN 122. This video is going to cover chapter 6, which covers inductors and capacitors. This is going to be a relatively short video, because here there's only there's like what, literally just 2 pages worth of slides, and there's not really too much explanation when it comes to this. This is also another part where you just have to memorize formulas, right? So now we are learning about capacitors and inductors, right? So a capacitor stores voltage right here. This, you see, capacitor stores voltage, inductor stores current, right? So with your capacitor, what happens is that the way it charges like this, right? The current charges your capacitor like this, from the positive to the negative. But as soon as you disconnect your battery source, then the current of the capacitor flows exactly like a battery does, from the negative to the positive node. This is something that is very important. You must remember this, right? That when you disconnect your source, the current is going to flow as if it was flowing from a battery, from the negative to the positive of your capacitor. Okay? And the one thing that's weird about capacitors, when they're in parallel, you add them up. So C equivalent is equal to C1 plus C2 plus C3 plus whatever. And when they're in series like this, it's 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus, So with capacitors, when they are in parallel, to find the equivalent, you add them up as if they're in series. It's series resistor. And when they're in series, to find the equivalent, you treat them like parallel resistors. Okay? And memorize these 4 formulas. Alright? That's capacitors in a nutshell. These 4 formulas, you are going to be using a mix of them. They could either give you they could either give you a charge, and then you need to find the capacitance of the capacitor, and then they ask you to do some KVL or some KCL to find the voltage across, something like that. Or these 2 formulas with the I and V, they're not used that much yet. They are used when it comes to your AC and your DC analysis, but that's going to come in more later, after we have learned about phasors and chapter 9 stuff, right? So for now, know that these 2 formulas exist, and we will use them a little bit later. We're not going to go into depth right now about them, and we are going to just know that they exist. And because we can't go into them without you actually understanding phasors first, and phasors are going to be explained in the next chapter. And that's not really going to be an explanation. It's also going to be like this, where I point and I say stuff, and I expect you to know what phasors are, but I'm going to give you a very brief introduction on what phasors are. But at the end of the day, phasors are something that you should have covered in WTW, or are going to cover in WTW. And as this is a course for electronics, and I'm not a mathematician, I'll just give you a quick run through of how I understand it. It might not be the correct, proper pruned way to do it, but I'll just try to give you a summary of what it is when you get to that point. But for right now, this and these formula are the most important at the moment. These 2 will come in later. right? And then your inductor, what it does is it stores current. So even though, like, the one thing about your inductor, like, you see, to charge it is this way, and also when you disconnect it, it discharges the same way. It's not like the capacitor where when you discharge it goes in a different way. Okay, that's one thing you should notice about your inductor. And other than that, everything else is still the same. When you got series inductors, you treat it like series resistors. So this is R1 plus R2 plus R3 plus till infinity. And when they're in parallel, you treat it like parallel resistors. 1 over L equivalent is equal to 1 over L1 plus 1 over L2 plus 1 over L3 plus till infinity, right? And yeah, wait, shouldn't it be, am I, yeah, here are your three formulas here. Okay, so I just had to quickly pause the video because I realized that even I myself did not know that this is the formula for inductance. Because inductors isn't really something that you use that much in electronic engineering. You use them more in heavy current electrical engineering. So I have never ever actually have needed to know this formula, and I actually didn't put it on the slide because it's useless. I'm just putting it on here so that you can know that such a formula exists, but don't focus on that because I think that is a very stupid formula that you rarely ever use, right? So then I just put it here so that you know it exists, but there is no need for you to memorize this formula. But here your work is equal to half inductance times current squared. Your I is equal to 1 over L integral from t to t0, and these are the formulas that you should remember. Keep them in your brain. And as demonstrated last time, when I say memorize a formula, you should memorize it because when I do the examples, I'm going to heavily rely on the formula, and that's where things are going to come in. But so far the problems we're going to do based on just this inductor stuff is it's pretty simple. Okay, so let me just really try to explain how a capacitor works, right? Because I went through this pretty quickly, assuming that you have looked at this, but I realized that some of you might not have even seen what happens, right? So a capacitor stores your stores your voltage, right? So what you do is that you connect a voltage source to a capacitor, and eventually, after some time, your capacitor is going to gain so much charge that it's equal to the voltage, right? It's equal to the voltage source. Okay, I should put that on silent anyways. So what happens is this happens, right? And then what you can do is that usually, let's say there's like some elements here, like a resistor, right? So after doing this, now that this capacitor has stored voltage here, what you do is that you turn off the voltage, right? And then the capacitor drains into your resistor, and the capacitor works like a battery, and eventually the current finishes, right, at a pace of this e to the negative t. I need to put that like as shown by, okay, actually it's not, it's shown here, right? When you integrate this, you get something like this, where the current flows out at a rate like this, right? So yeah, that's the one thing about your capacitor. Your inductor does the same thing, just that it uses a inductor, right? So eventually it starts like this, and then after a long time you have it becoming like a short circuit type of thing, right? And then you can turn off the inductor. You can turn off the current source, and then the inductor will act like a current source, and it will drain into your resistor. And this is how inductors and capacitors work. They just store energy, and that's what they do, right? So you can use inductor in calculators. You use inductors, and as I said, electronic engineers, we don't really use inductors. We think inductors are stupid, because inductors are really stupid. They are bulky, they waste current, they make like harmonics. They are just terrible pieces of equipment. Therefore, like lazy electrical engineers who just like high current stuff, right? So here, and you can copy the way an inductor works by using capacitors, but that's like high level stuff. That's like something I learned in third year. And so if you look at this, right, you can see that the current is proportional to the capacitance multiplied by the derivative of the voltage. So therefore, by using a capacitor, you can find derivatives, right? So therefore, you can find derivatives like calculator. If you are looking for a derivative of something, you can use a capacitor. All you do is just you time how fast the voltage is dropping through the capacitor, and then you can find the derivative of something, right? If you look at the current, if you look at the voltage, you can find the integral of something, right? So these are things that these are ways you can use your capacitors to now make more complex circuits. These are integrators, and these are differentiators. That's terms that you refer to them as. And for all electronic and electrical engineers, this is gonna be your life. Know how capacitors work. And for everybody else, like capacitors are pretty important. Like the way, they're very important. Capacitors and transistors are literally everything in circuits. And that's it. And the highlight of this is when it comes to inductors, when it comes to caps, learn all four of these formulas, right? So know this formula, that formula, that formula, that formula, and know that when you got caps in parallel, they act like series resistors, and when you got caps in series, they act like parallel resistors. And here for inductors, all you need to know is these three. Do not worry about that fourth formula. I put it on there because I'm sure there's one guy who's just like, how do I calculate the inductance of an inductor? And I'm just like, that doesn't matter at all. Nobody does that. And that's that formula. But at the end of the day, you never know. You might just get struck by lightning the day before your test, and this question might come up. But this is like a 1 in a million chance that it might come up, and they would have to literally say that there's a piece. Let me just explain this formula, because I honestly think it's stupid that I'm doing this, but I'm still gonna do it because I like electronics. So I just copied that formula. So this is how an inductor works, right? Imagine a bar, a thin cylindrical iron bar, right? That is a length of L long. So from here to here is L long, right? So you've got this bar, right? And you just like, I'm going to take this piece of wire and I am going to wrap it all around you, like chup 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 chup, right? And this wire, I'm going to wrap it like 50 times. That's the number of turns, the number of full circles it makes around. And this bar has an area here, a cross-section area of A is equal to pi r squared, and mu is the conductivity. This is conductivity, something you're going to learn in NMC in material science, but this is basically how you make a conductor. You take a piece of iron, like let's say an iron nail. Like you go and get a nail, like you take a nail, take a piece of wire, wrap it around a couple of times, chup 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 chup, right? And then you measure the radius of your nail, and then you calculate the area, and then you go on Google and like, what is the conductivity of an iron nail? And then using that, you can calculate the inductance of the inductor that you just made. Making an inductor is easy peasy lemon squeezy. Anybody can do it. And yeah, like yeah, you should actually try this at home. It's pretty cool. It's pretty cool. And yeah, that's it. This video didn't need to be this long. It could have simply been 2 minutes long, where you point at the equations if this is important. But this is supposed to be informative for people who want to learn. And yeah, at the end of the day, here, remember this, remember this, remember this. That is not important. Well, I think it's not important. I'm going to consult the semester tests, like the future semester tests, because when I was doing it, that wasn't an important formula. And as I said, I had to look back when I compiled these notes when I was making them, and then I didn't include this formula because I didn't think it was important, but I'm gonna look through past semester tests to see if a question like this comes up, where they say, hey, there's a piece of like iron and there's a piece of like coil. It's wrapped around the iron like 50 times. The coil has a length of this and there's an area of this. Calculate the conductivity. Like I don't see them asking a question like that. Cause like that's like literally a 1 mark question. But hey, you never know. Like for those people who are trying to grab that 50%, that 1 mark might be life or death. You never know. So yeah, that's it. Series inductors treat like series resistors. Parallel inductors treat like parallel resistors. Nothing new, nothing old. And yeah, we will do problems in the next video. And yeah, that's pretty much it.